Welcome! In this session, we'll explore the problem titled Verify Preorder Serialization of a Binary Tree. This problem challenges our understanding of binary trees and preorder traversal. Stick around as we break it down step by step and develop an efficient solution. In this problem, you're given a string that represents a binary tree's preorder traversal serialization. Each node in the tree is represented by a non-negative integer, while null pointers are represented using the hashtag character. Values are separated by commas. Your task is to determine whether the given string forms a valid serialization of a binary tree. To be valid, the binary tree must follow its structural properties, meaning each node can have at most two children. For input, you'll receive a single string called preorder, and your goal is to return a Boolean value, true if the serialization is valid, and false otherwise. Let's look at an example to understand this better. If the input string is preorder equals 93 for hashtag 1 hashtag 2 hashtag 6 hashtag, then the output is true. Here's why. This string represents a binary tree where the root node is 9, and it has two children, 3 on the left and 2 on the right. Node 3 has two children as well, 4 and 1, and so on. In this tree, every node has at most two children, and the structure follows the rules of a preorder traversal. Therefore, the serialization is valid, and we return true. Now consider a different example where the input is preorder equals 1 hashtag. In this case, the output is false. Here's the explanation. The string implies that the root node is 1 and is followed by a single null pointer hashtag. However, a valid binary tree requires every node to have either 0, 1, or 2 children. Here, the root node is missing its right child entirely, making the serialization invalid. As a result, the output is false. Another example to consider is preorder equals 9 hashtag 1. For this input, the output is also false. This is because the null pointers hashtag that follow the root node 9 indicate that it does not have any children. However, the presence of a subsequent non-null node 1 violates the preorder traversal structure. In a valid binary tree, once null nodes are encountered, no further nodes should appear. This discrepancy makes the serialization invalid, so the output is false. To determine validity efficiently, we can keep track of available child slots throughout the serialization process. Each non-null node adds 2 slots for its potential children, while each null node consumes 1 slot. By ensuring these slots are managed correctly, we can verify whether the serialization satisfies the properties of a valid binary tree. For example, in a valid serialization, the total number of null nodes must always be 1 more than the total number of non-null nodes. This observation forms the basis for solving the problem. To tackle this problem, the first approach we can consider is the brute force method, which involves simulating the construction of a binary tree based on the given preorder serialization. The intuition here is that since the input represents a preorder traversal, we can try to reconstruct the tree step by step. Starting from the root, we recursively process the left and right children, validating whether the structure adheres to the rules of a binary tree. To implement this, we first split the input string by commas to separate the nodes. Then, as we process each node, we return true if we encounter a null node, represented as a hashtag. For non-null nodes, we recursively validate both subtrees. Finally, we ensure that all nodes in the input have been consumed without leaving any extras. While this approach is intuitive, it has significant drawbacks. The repeated slicing of the input string during recursion leads to a time complexity of O(n)², and the recursion stack can consume up to O(n) space in the worst-case scenario. This makes it impractical for large inputs, highlighting the need for a more efficient approach. An alternative and more efficient strategy is the stack-based approach, which revolves around the concept of tracking available slots for nodes. Here's the intuition. In a binary tree, each node occupies 1 slot, but non-null nodes also create 2 new slots for their children, while null nodes consume a slot without creating any. By keeping track of these slots, we can validate the serialization dynamically. We start with 1 slot for the root node. As we iterate through each node in the input, we decrement the slot count since the current node occupies 1. If at any point the slots become negative, it indicates an invalid serialization, as there are more nodes than available slots. For non-null nodes, we add 2 slots to account for their children. At the end of processing, we check if the slot count is exactly 0, ensuring all slots have been perfectly filled. This method is highly efficient with a time complexity of O(n), as we traverse the input only once, and a space complexity of O(1), since we use just a single integer to manage the slots. The stack-based approach is not the only alternative. Another method we could use is count-based validation. The key observation here is that in a valid preorder traversal of a binary tree, the number of null nodes will always be exactly one more than the number of non-null nodes. This property lets us validate the serialization with a simple counting mechanism. As we traverse the input, we maintain two counters, one for null nodes and another for non-null nodes. At the end of the traversal, we check if the null count is equal to the non-null count plus 1. This approach is straightforward, with a time complexity of O(n), due to a single pass through the input and a space complexity of O(1), since only counters are used. However, while it's simpler to implement, it's less intuitive than the stack-based approach and doesn't provide real-time feedback about the structure of the tree during the traversal. Among the approaches discussed, the stack-based strategy stands out as the optimal solution for this problem. It directly models the concept of slots required for a valid binary tree, making it both intuitive and computationally efficient. With a time complexity of O(n) and a space complexity of O(1), it is well suited for handling large inputs. Compared to the brute force method, it eliminates the inefficiencies of recursion and string slicing, significantly improving performance. Furthermore, while the count-based approach is simpler, the stack-based method offers a clearer and more dynamic validation process. It allows us to detect invalid cases early, such as when the slots go negative during traversal, avoiding unnecessary computation. This real-time feedback makes it easier to debug and understand the tree structure as we process the input. While the stack-based approach is highly efficient and elegant, it does come with a minor trade-off. The concept of managing slots may not be immediately intuitive to beginners. However, once understood, it provides a powerful framework for solving the problem. Its significant performance advantages, coupled with the ability to detect errors dynamically, far outweigh the slight learning curve. In conclusion, this approach strikes an excellent balance between efficiency and clarity, making it the ideal choice for validating a binary tree's preorder serialization. By leveraging the slot mechanism, we ensure not only correctness but also early detection of invalid scenarios, demonstrating why this method is the most robust solution available. To understand this problem, we need to validate if a given string, which represents the preorder traversal of a binary tree, can actually form a valid binary tree. In this context, the input string uses commas to separate nodes, and null nodes are represented by the symbol hashtag. For example, the string might look like 93 for hashtag comma hashtag 1 hashtag comma hashtag 2 hashtag 6 hashtag comma hashtag. The first number represents the root, followed by the left and right subtrees in preorder sequence. One brute force approach to solve this involves simulating the construction of the tree. First, we parse the input string into an array of nodes by splitting on commas. This makes it easier to process each node one by one. Then, we define a recursive function, build_tree, which attempts to construct the tree by processing the nodes in sequence. The base case in this function is that if the current node is hashtag, it means we've reached a null marker, so we return null and move to the next index. Otherwise, we treat the current node as a valid tree node and continue building the left and right subtrees recursively. In the recursive tree construction, the left subtree is built first, and after processing it, the index is updated to ensure we are working on the correct position for the right subtree. Similarly, once the right subtree is processed, the index is updated again before returning it. This ensures that each node and its children are processed sequentially without skipping or overlapping. After the recursive process completes, we validate the result by checking if the index matches the end of the node array. If the index doesn't align with the length of the array, it indicates that there are extra nodes left unprocessed, making the input invalid. Some edge cases further clarify this approach. If the input string is empty, it is immediately invalid. If the input contains only hashtag, it's valid since it represents an empty tree. Finally, mismatched nodes and null markers will naturally fail during validation, as the recursive function won't process them correctly. These insights highlight the importance of preorder traversal, where nodes are processed in the order root, left, and then right. The null markers hashtag allow us to distinguish between missing children and valid nodes, while the index tracking ensures every node is processed exactly once. To implement this approach, we rely on two primary data structures. First, an array is used to store the split input string, making it efficient to access nodes by index. Second, the recursive stack is implicitly used during the tree construction process. This stack keeps track of the current node being processed and its associated children, allowing the algorithm to backtrack and process subtrees correctly. In terms of complexity, the time complexity is O(n), where n is the number of nodes in the input string. Each node is visited exactly once during the recursive traversal. The space complexity is O(h), where h is the height of the tree, as this accounts for the space required by the recursive call stack. Here's a quick pseudocode outline of the recursive function. The function build_tree takes the current index as an argument. If the index exceeds the array length, it returns null. If the current node is hashtag, it also returns null and moves to the next index. Otherwise, it creates a new tree node, recursively builds the left and right children, and then updates the index accordingly. After constructing the left and right subtrees, the function assigns them to the respective child pointers of the current root node and then returns the root along with the updated index. The main function is _valid_serialization, splits the input string into an array of nodes and calls build_tree starting at index 0. Finally, it validates the input by checking if the returned index matches the length of the array. The key operations here include splitting the string into an array for easier processing, recursively simulating preorder traversal to build the tree, and validating whether all nodes were processed correctly. To optimize this process, null checks can be handled inline to avoid creating unnecessary tree node objects for null children. This helps improve efficiency without altering the overall logic. Another optimization involves replacing the recursive approach with an iterative one to reduce the space used by the recursion stack. However, this can make the implementation more complex and harder to follow. Let's also review some edge case examples to solidify our understanding. For the input 9(3) for ##1 #2 6 #, the tree is valid and represents a balanced binary tree. For one hashtag, it's invalid because a root node cannot have only one child. The input hashtag is valid, as it represents an empty tree. Lastly, for 9 #1, the tree is invalid because there is an extra node, 1, after the tree construction is complete. These examples demonstrate how the algorithm handles different scenarios and ensures the correctness of the input. This Python implementation solves LeetCode problem number 331, verify preorder serialization of a binary tree, using a simulation-based approach to track available slots in a binary tree. The input string represents the preorder traversal of a binary tree with commas separating nodes and hashtag indicating null nodes. The isValid serialization function begins by initializing slots to 1, representing the initial slot for the root of the tree. The preorder string is split into nodes using commas. Each node is processed sequentially, and the number of slots is adjusted as follows. 1. For every node, a slot is consumed, decrease slots by 1, as each node occupies one slot. 2. If at any point slots becomes negative, the serialization is invalid, and the function immediately returns false. 3. If the node is not a null node, hashtag, it contributes 2 new slots for its left and right children, increase slots by 2. After processing all nodes, the function checks if slots is 0. If yes, the serialization is valid, otherwise, it's invalid. This ensures that all slots were properly allocated, and no extra nodes or unused slots remain. This solution is efficient, with O(n) time complexity, where n is the number of nodes in the input string, since each node is processed once. The space complexity is O(n), due to the splitting of the string into a list. The algorithm handles edge cases such as empty trees, hashtag, trees with excessive null nodes, and invalid input strings effectively due to the slot tracking mechanism. Here, we have the Java implementation of the solution to verify the preorder serialization of a binary tree. First, we define a method called isValid serialization, which takes a string input representing the preorder traversal. We initialize a counter called slots to 1. This counter keeps track of the available slots in the binary tree, starting with one root slot. Next, we split the input string by commas into an array of nodes to process each node individually. Then, we iterate through the nodes using a for loop. For every node, we decrement the slots counter by 1 because each node occupies a slot. If, at any point, the slots become negative, it means the serialization is invalid, so we immediately return false. Finally, if the current node is not null, represented by a hashtag, it contributes 2 additional slots, as a non-null node can have 2 children. At the end of the iteration, we check if all slots are used up, which would mean the serialization is valid. A valid serialization ensures that the number of slots becomes exactly 0. If the slots are not 0, it indicates that the binary tree structure is incomplete or has extra nodes, so the serialization is invalid. The method then returns true or false based on this condition, completing the implementation. This approach ensures an efficient and concise validation of the preorder serialization string. In this example, we are given the input string 9-3 for hashtag comma hashtag 1 hashtag comma hashtag 2 hashtag 6 hashtag comma hashtag, which represents a preorder traversal of a binary tree. The goal is to determine if this serialization is valid. We start by initializing the slots variable to 1. This represents the available slots for nodes, and initially, we need 1 slot for the root node. Next, we split the input string into individual nodes, resulting in the array 9, 3, 4, hashtag, hashtag, 1, hashtag, hashtag, 2, hashtag, 6, hashtag, hashtag. Now, we process each node in order. The first node is 9. Since it's a valid value and not a null marker, hashtag, it consumes 1 slot, reducing slots to 0. Then, because 9 is not null, it adds 2 new slots, bringing the total to 2. Moving forward, the second node, 3, also consumes 1 slot, reducing the count to 1. As it's not null, it provides 2 additional slots, so the slot count increases to 3. The third node, 4, follows the same logic. It consumes 1 slot, leaving 2, and adds 2 more slots, resulting in 4. This process continues for each node in the string. Next, we process the fourth node, which is hashtag. The null marker consumes 1 slot, reducing the available slots to 3. Since it does not represent a valid node, no new slots are added. Similarly, the fifth node is also hashtag, consuming 1 more slot and leaving us with 2 slots. Again, no additional slots are added. The sixth node, 1, is then processed. Being a valid node, it consumes 1 slot, reducing the count to 1, and adds 2 new slots, increasing the total to 3. We continue processing the remaining nodes in the same manner, updating the slot count accordingly. Once all nodes have been processed, the slots variable reaches exactly 0, which indicates that the serialization is valid. This is because all available slots have been matched with the appropriate nodes, and no extra slots are left over. Therefore, the output for this example is true. Here, we look at an example where the serialization is invalid. The input string is 1 hashtag. We begin by initializing slots to 1 and splitting the string into nodes, resulting in the array 1 hashtag. The first node is 1, which consumes 1 slot, leaving us with 0 slots. Since 1 is not null, it adds 2 new slots, bringing the total to 2. Then, we process the second node, hashtag. Being a null marker, it consumes 1 slot, reducing the count to 1. However, no additional slots are added because hashtag does not represent a valid node. At this point, there are no more nodes to process, but we still have 1 slot remaining. This means that the preorder traversal left an unmatched slot, which violates the rules of a valid serialization. As a result, the output for this example is false. Now, consider another invalid example where the input is 1 hashtag comma hashtag comma hashtag. After initializing slots to 1 and splitting the input into nodes, we get the array 1 hashtag hashtag hashtag. The first node, 1, consumes 1 slot, reducing the count to 0. Since it's a valid node, it adds 2 additional slots, bringing the total to 2. The second node, hashtag, then consumes 1 slot, leaving 1. As a null marker, it does not add any new slots. Next, the third node, another hashtag, consumes 1 more slot, this time reducing the count to 0. Again, no new slots are added because hashtag is not a valid node. At this stage, we still have 1 more node left to process. Finally, we process the fourth node, which is hashtag. This null marker consumes one slot, but since the slot count was already 0, it pushes the slot's variable into a negative state, specifically -1. A negative slot count indicates that the preorder serialization attempted to assign a child node where no slot was available. This violates the rules of a valid binary tree structure, and we can terminate the validation process early. The output for this example is false. To summarize the key insights, the slots variable tracks the number of available slots for nodes, with each node consuming one slot. Non-null nodes add 2 slots, representing space for their children. Any point where slots becomes negative or does not equal 0 at the end of processing indicates an invalid serialization. The time complexity of this solution can be understood by breaking it into 2 main operations. First, we have the preorder.split, operation, which converts the input string into a list of nodes. Since this operation processes each character in the string, and the input contains n nodes, it takes n time. Next, we iterate through the list of nodes using a for loop. Within this loop, all operations such as decrementing the slots variable, checking the condition if slots 0, and updating slots for non-null nodes take constant time, or O1, for each iteration. Since the loop processes all n nodes, this contributes n to the total time complexity. Combining both steps, splitting the input and iterating through the nodes, we get an overall time complexity of n. Adding up the time complexity of both operations, n, from splitting the string and n, from iterating through the nodes, we arrive at a total time complexity of n. This means the algorithm is linear with respect to the size of the input. Now, for the space complexity, the largest contributor is the storage required for the nodes list created by preorder.split, This list contains n elements, where n is the number of nodes in the input, and therefore requires n space. Additionally, the algorithm uses a few auxiliary variables such as slots and node, which require constant space, or O1. Combining these components, the total space complexity is n plus O1, which simplifies to n. The memory usage of this algorithm is primarily determined by the storage required for the list of nodes, which dominates the space complexity. Looking at the algorithm's behavior under different scenarios, the best case occurs when the input represents a minimal binary tree, such as a single hashtag for an empty tree. Even in this case, the algorithm splits the input and processes it, resulting in n time and n space. In the average case, where the input represents a balanced binary tree or another valid structure, the algorithm still performs n operations and uses n space. Finally, the worst case occurs with a long string containing many nodes, possibly invalid, such as one with all non-null nodes and no terminating hashtag. Even in this scenario, the algorithm's time and space complexity remain n, making it consistent across all cases. To understand why this approach is efficient, let's compare it with a more naive or brute force solution. A brute force method might involve explicitly constructing the binary tree from the input string and then validating its structure. Tree construction would require parsing the entire input and creating nodes, which would take n time. Once the tree is constructed, validating it would require a traversal of all nodes to ensure the structure is correct, adding another n time. Moreover, representing the tree in memory would require n space for the nodes. While the time and space complexities of the brute force approach would still be n, the constants involved would be significantly higher due to the overhead of constructing and traversing the tree. The given solution avoids this overhead by using the slots mechanism to validate the input directly, making it more practical and efficient. Finally, let's solidify the understanding of the big O complexity. The algorithm processes each node in the input exactly once, performing constant time operations, which confirms the n time complexity. For space, the main contributor is the nodes list, which is proportional to the size of the input, resulting in n space complexity. The auxiliary variables, requiring O1 space, do not grow with the input size and therefore do not affect the overall complexity. This solution is optimal for this problem, as it achieves linear time and space complexity, which cannot be improved further given the need to process each input node at least once. When tackling this problem, there are several common mistakes to avoid. First, it's important to correctly interpret the input format. The string provided represents a preorder traversal, not an inorder one. Misunderstanding this will lead to incorrect reconstructions and failed validations. Next, edge cases are critical. Situations like an empty string or a tree with only one node must be handled properly. Ignoring these can cause runtime errors or inaccurate results. Another frequent issue is overcomplicating the simulation. Sometimes, people unnecessarily build a full tree, which increases space complexity without adding any real benefit since the task is just to validate the traversal. Finally, improper stack usage in iterative solutions is another pitfall. For example, popping the stack prematurely or not pushing the right nodes can cause validation failures or result in incorrect tree structures. Each of these mistakes highlights the importance of a clear understanding of the problem requirements and efficient algorithm design. Another frequent mistake is ignoring constraints on node values. Don't assume all node values are positive integers. Problems may include negative values or even strings as valid node representations. Failing to account for this can lead to parsing errors or an incomplete solution. Shifting to interview strategies, binary tree traversal problems often require good pattern recognition. Preorder, inorder, and postorder traversals all have distinct properties, so being able to differentiate and apply them effectively is a key skill. It's also crucial to distinguish between simulating the construction of a tree and validating a traversal. Validation is faster and more memory efficient, as it avoids unnecessary data structures. Additionally, always clarify edge cases during an interview. For example, ask about empty inputs or unusual formats. Finally, space optimization is worth considering. Iterative solutions using a stack are often better than recursion, as they avoid issues with recursion depth while keeping memory usage low. Expanding your understanding of this problem can be helpful by exploring related problems. For instance, in LeetCode 297, you serialize and deserialize a binary tree, which involves turning the tree into a format like a string and reconstructing it. LeetCode 105 and 889 focus on constructing binary trees from different traversal combinations, such as preorder and inorder or preorder and postorder. These problems build your intuition for how traversal orders affect tree structure. Additionally, alternative approaches can be considered. Recursive simulation is a common strategy for constructing or validating trees. It's intuitive and easy to implement, especially for smaller inputs. However, it has a notable downside: recursion depth limits can cause stack overflow for very large inputs. This is an important trade-off to keep in mind when choosing an approach. Iterative stack-based validation can be a more robust alternative. This method is more space-efficient than recursion and avoids stack overflow issues entirely. However, it requires precise handling of the stack, as improper operations can easily lead to incorrect results. Another highly efficient technique is one-pass validation without actually constructing the tree. This approach is both fast and memory efficient, making it ideal when the goal is to validate the traversal rather than build the tree itself. The downside, however, is that it doesn't allow you to retrieve the full tree structure. Each of these approaches has its own strengths and weaknesses, so selecting the right technique depends on the problem's specific requirements and constraints. Great job following along. Today, we reviewed how to verify preorder serialization of a binary tree by simulating tree construction. Remember, understanding traversal orders and edge cases can make or break your solution. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!